Everybody.
Good evening, sir.
Good evening, sir.
Well done, sir.
Yeah, thank you. We start now.
Okay.
So we have been discussing inferential statistics. The last time we talked hypothesis testing as a form of inferential method. We are discussing the second method, which is confidence interval. So today we'll be looking at confidence interval. So these are the issues we'll be looking at under confidence interval: point estimate and interval estimate, confidence level, confidence intervals of means, proportion and rate, confidence interval of the difference. So for us to understand what estimate means, the meaning of estimate, point estimate, and interval estimate. What do you mean by parameter estimation? You get to know that as a researcher, you are interested in what is happening. You are interested in the summary in the population. The summary in the population is the parameter. Why you don't have access to the whole population, whatever summary you can make is statistic. So from the statistic, you want to know what is happening about the parameter. So whatever you get with your sample is an estimate. That statistic is an estimate of the population parameter. So when we talk about parameter estimation now, we are trying to estimate what is in the population with what you have in the sample. And whatever you have, you're able to estimate in the sample is called statistic. So you just want to make judgment or extrapolation from the sample statistic to the population parameter. That is the realm of inferential statistics. So when we talk about parameter estimation, there are two factors that determine the type of estimate or the way you do the estimate. One would be the type of variable. Are you dealing with quantitative variable or categorical variable? The second one is the group. Are you dealing with one group or more than one group? Even when it is more than one group, you're having two groups. Are they independent groups or they are dependent groups? All these issues we have discussed them in some of our lectures. We'll still continue making mention of them. So like now, if you look at this slide, you see that the number of groups here, you are dealing with one, with what we usually call descriptive study, only one group. Now, in that one, the estimate, the parameter of interest, is this something is it quantitative that you can summarize with mean and standard deviation, or is it categorical that you summarize with percentage or proportion? So now, when you are dealing with one group, it's either you summarize with mean. If it is, that's continuous variable. If it is dichotomous variable, here we just put dichotomous so that it should not confuse people. Here, whenever we talk about categorical, you can always treat any categorical as dichotomous. Dichotomous just means two possible values, either male or female. Then everything categorical can be treated like that. For example, you say ethnicity in Nigeria, you can list all the, even if they are 200, it's categorical. But you can say Hausa and others. So Hausa stroke others, they become dichotomous. That is, if you want to say, is it Hausa or not? Is it Yoruba or not? Igbo or not? Is it Chekri or not? When you remove one category, compare with the remaining, you have dichotomized it. You have put the remaining under one umbrella, while this other one separate umbrella, making it two categories. And most of the time when we do analysis, it's like that. So, like for example, what is the proportion of female? What is the proportion of male? What is the proportion of a particular ethnic group? What is the proportion of South-South, a particular geopolitical zone in the ministry? So, anything categorical can be summarized as dichotomous or binary. So here, for that, you see proportion, rate, prevalence. There is a prevalence of hypertension. prevalence of anemia, the prevalence of a particular type of cancer, cumulative incident rate. And the rate is a proportion you measure over time. When time factor comes in, it becomes rate. So I think under when we're summarizing categorical variable, under our descriptive statistics, we talk about that you summarize categorical variable with ratio. Ratio is whatever where you are dividing two items of the same unit. So the ratio, like male-female ratio, the number of male, number of female, that's the ratio. There is special form of ratio. The special form of ratio is when the numerator is also part of the denominator. Like what is the proportion of female? The numerator is the female, number of female, but the denominator is the number of female plus the number of male. So it's not male, female, female, male now. It's female over the total. Since that female is part of the denominator also, so that is a proportion, part of a whole proportion. When you measure, you can measure the proportion in decimal, you can measure it in percentage. It's a matter of multiplication by 100. We know that. Then if this proportion you measure, if it's measured over time, it's rates. Either over 1 week, over 2 months, over even if it's over 2 minutes. Once you put in the element of time, it's rate. Over a year, over 2 years, it's rate. So now, when we come to two independent samples, when you have two groups, we have looked at one sample now. If it is two independent, because two samples can be independent or dependent. The difference between dependent and independent is independent means there are two separate subjects. Like when you sample urban rural, they are independent group because the people you sample in urban, they are different from the people, the subject you are attended to in urban, they are quite different. There is no person that was in urban that was in rural. They were separate subjects. So the sample was separate, contains separate people. That is what we call independent sample. The dependent sample means it's the same people. So if we are talking of the sample now, actually you are talking of the data you have collected. Imagine the same group, you measure their hemoglobin concentration or you measure the blood pressure, and you later come back, maybe after you have done something, you measure the blood pressure of the same set of people and record it. If it's the same set of people you measure before and after, it's dependent. So in the same group, actually, when they are talking of group, you are talking of the data you collected. Because you have a group of data you collected the first time, you have the second time, dependent. So the way you summarize differ. So if you are having two independent groups now, you are looking at the different. If your outcome variable is continuous, something that's numerical. If you want to look at the difference between the two groups, it's different in the mean. So like for urban rural, you measure the concentration of hemoglobin concentration. Hemoglobin concentration, the mean for urban, mean for rural, you may get different value. So you can summarize the two. So when you're not looking at the difference, x minus s bar minus s bar 1 minus s bar 2, you can remove, you can look at the difference. If one is 15, one is 13, you can see the difference too. So you can say 15 minus 13. So that is the difference in the mean. But if it is two dependent, if it is the same people you measure the hemoglobin concentration before and after, you are talking of, yes, you measure it now, maybe the average is 13, you measure it again, it's 15. But because it's the same set of people, so actually the mean is not, you may measure it, you see 15, 13, but that's not what, you are not going to remove 13 from 15, it doesn't make sense. What makes sense is that for each of them, since you measure them on two different occasions, if there are 200 sample, 200 people, the 200 people, for each of them, you remove the value before and after, the value before and after. The difference is you now calculate the mean. That's the mean difference, or mean. Sometimes you call it mean of the difference. I prefer calling mean of the difference. Why the other one, the independent group, instead of say different in mean of different of the mean. It's not mean of the difference. But this one now, the mean of the difference is different between mean. When you have two mean, you remove one from one. That's different in the mean. That is different between the two. But the other one that you have to first of all remove value before and after, from maybe after from before, before from after. For all of them, before you calculate the mean, that's the mean of the difference. So for each of them now, the way you estimate differ. For example, now, when you are dealing with two independent groups, if the variable of interest is dichotomous, is categorical, you'll be looking at different in the proportion. The percentage of this one minus percentage of this one, different in the rate, different in the risk. Attributable is all those different descriptions. Now, that's parameter estimation. You see that whatever you are doing with your sample, you are trying to estimate the parameter in the population. Now, let's now know this. What is this estimate? What you are estimating is actually in the population is the parameter you are estimating. But the estimator, what are you using to estimate? Because you don't know the parameter. Yes. What do you use to estimate? Is the statistic from the sample that serves as estimator. And parameter is what you want to estimate. The result you get is the value, is the estimate. It's an estimate. You are not 100% sure that that is the same value in the population. It's an estimate of the population parameter. So we want to estimate parameter. Whatever you get is an estimate. But the estimator, what you are using to estimate, is the statistic that you have access to in your sample. So this one is look at if your parameter of interest is mu, which is the mean in the population, bar x, which is the mean of the sample, is the estimator. If the parameter of interest now is the variance, this one is variance in the population. This is the variance in the statistic in the sample, which is the estimator. Of course, S square, this is rho square. This S square, S, if you remove, find the square root, that's standard deviation. S will be standard deviation in the sample, where this row without the square will be the standard deviation in the population. Now, we have understood the meaning of, let's differentiate between point estimate and interval estimate, because that's where the issue of confidence interval comes in. We have understood the estimate, but what is point estimate? The point estimate of a population parameter is a single value of a statistic. When you use statistic to estimate the parameter. So if you calculate only one value, like mean, just the mean blood sugar is 65, that is a point estimate. If you calculate, you want to know the prevalence of anemia, and you say the prevalence of anemia is 30%. That 30% is an estimate, it's a point estimate. The interval estimate is defined by two numbers between which a population parameter is said to lie. In interval estimate, that you give two values. So in other words, you give a range of values within which you believe that the population value will be in between. That's just it. So it is easier. So point estimate is just one figure. Interval estimate, two figures that give a range of. Okay, if somebody said, I want to guess somebody's age. I said, okay, your age, maybe the person is 35. I just say, I just look at it and say, you look like 32. No, I miss it at once because I'm giving a point estimate. But if I say, oh, your age will be between 28, 37. In that situation, the person is 35. I have given a range of value, which you see that I'm able to capture. So if somebody just give, you just want to get somebody to say, just give one value, and the person that just give a range of value, the person that gives a range of value will likely capture, at least even if you don't say it directly, capture the value. And if I see, say, okay, I say between 20, I can just say maybe between 31 and 34. You see that I have given a range of value that is very narrow, and I still miss it. But the one I gave that is larger, like wider, which is 28 to 37, was able to contain the value, the real value. So that is just an illustration of why we use interval estimate. It's preferable to point estimate. And you now know that the interval estimate also, they are different with the level of confidence. If you look at it, I gave two examples. When the wider the interval, the more confidence you have that you're able to capture the value. This is just a graphic illustration of what I just said. The point estimate is just one value, middle, yeah. But the interval estimate, two value, you can be sure that after calculating, it is after you have calculated the point estimate that you now calculate the interval estimate from the point estimate. Interval estimate will be less, and the lower value will be less than the point estimate. The higher value will be higher than the point estimate. So the point estimate will be in between the lower and the upper limit of the interval estimate. And since the interval estimate is a range of value, the lowest one is the lower confidence limit, lower limit. The upper is the upper limit. Now the word confidence now comes in, because based on the width of the interval given, the width determines the level of confidence you have that this interval contains the population value. So there is a reliability factor now, which then give you the level of confidence. Now, we have talked about estimates. We want to now talk, we have talked about point estimate and interval estimate. Let's now talk about this confidence interval. The confidence interval is a form of interval estimate. It's a range of value now that's likely to include a population value with a certainty or certain degree of confidence. So there must be that certain degree of confidence is the reliability factor. So if the confidence level of confidence is very slow, it's not as reliable as one with higher level of confidence. So it is often expressed, the confidence, that reliability factor, which is the confidence, is expressed in percentage, whereby population parameter lie between an upper and lower interval. This graph is just to give you a picture of it. You can see this, you have a value, a point estimate. The parameter of interest is the mean. The mean in the population. This is the mean 4.27. Estimate you're able to get from your point estimate is 4.27. But to calculate the interval estimate, you now have a value below the lower, we have the lower limit and upper limit. And to introduce the level of confidence, here now the level of confidence in this picture or in this graph is 95%. You are 95% sure that this estimate I have given, the range of value, contain the population value by 95%. So all this will give you a picture of, okay, this thing I'm trying to look at in the population parameter, even though you cannot be 100% sure that this is the value because you don't have access to the whole data in the population. You only have access to sample data. Now, let's proceed. How do you compute this confidence interval? You see now, you're going to see later. You know, we talk about testing, which we discussed the last time. This is confidence interval, and there are different methods of there are different inferential statistics. There are different inferential methods. Sometimes we report them together. But the issue there is that both of them, they are doing the same thing in different ways, but as you're going to see, you will prefer one to the other when you see the output of both of them, comparing both of them. And that's the last thing we're going to do. Now, how do you compute this confidence interval? The point estimate plus that Z you are seeing is what represents that level of confidence or the reliability factor, multiplied by the standard error of the point estimate. Can you see now? So you have your point estimate, like for example, the mean value we saw the other time. Now, for you to calculate the interval estimate for that point estimate, you need to know, okay, that point estimate plus or minus a reliability factor times multiplied by the standard error. We have already in our initial lecture on this inferential statistics, we have discussed standard error as the standard deviation of sampling distribution, which actually measures the level of variability in the population. You can say, okay, whatever you measure, how does it deviate from the population value? Just the summary. So it's because it is believed to be equal to the population standard deviation. So if you measure an estimate, how does this, is it likely that this estimate differ from how different is it? How much deviation does it have from the real population parameter? So we have already established before that when you have small standard error, it means your estimate is close to the parameter. When you have a very big or large standard error, it means that your estimate is far from the parameter. We also said that another thing about standard error is that when it is very small, it may also mean that the attribute concerned does not vary much in the population. But if it's very large, it may mean the attribute very much in the population. But the first one is the most useful aspect of it. It actually shows that whether your estimate is far or close to the population. But you look at it now. In order for you to know, okay, how do you know the interval? How will you calculate interval estimate, confidence interval? You have introduced that standard error. The Z is the value for the standard normal distribution for the selected confidence level. You know, we talk about the confidence level you have. So if you choose 95, you can choose 90, 99, but nobody work with 90, but most of the time it's 95, then 99. The Z for 95 is 1.96. This, I've already said it, that Z is also known as reliability factor. In practice, we often do not know the value of the population, of course, population standard deviation itself. So, however, if the sample size is large, when it is greater than or equal to 30, then the sample standard deviation can be used to estimate our standard deviation. Now, if you want to do this thing now, standard error now is him for you to estimate. You want to estimate the confidence interval now. Standard error comes in, and we already established the fact that standard error is standard deviation divided by square root of sample size. So we move further. I just want us to see, because this graph we are seeing here will be shown under probability, normal distribution, under normal distribution. Just for you to remember that when something follows normal distribution, it has been proven. We have said it before. We know that the normal distribution, this one is a standard normal distribution. We say something follow normal distribution, it may give you the same shape, but different graph. But if you calculate the z, the number of standard deviation away from the mean, you now use to plot, it gives you one graph that is called normal standard curve. And this is the normal standard curve now. This normal standard curve is the most important thing in statistics, because if you remember also when we started discussing this inferential statistics, we talked about central limit theorem, which states that the statistic of the distribution of certain statistic, the sampling distribution of certain statistic tend to normality, especially if the sample size increases, irrespective of the original shape. What it means that even something that did not follow normal distribution, the variable that did not follow normal distribution, the statistic, the summary, what to summarize, whether mean, even its proportion, whatever you summarize, during your descriptive statistic, if the sample size increases, the sampling distribution, that is the sampling distribution, means that if, let's say, you sample many a time, the pattern will follow normal distribution. So that is what central limit theorem. That is why this normal distribution is the most important distribution in statistics and research, because everything still tends to that normal distribution. Now, having established that this normal distribution is bilaterally symmetrical, we have already said that it has been proven theoretically that in between -1 and +1, you know, the horizontal now scale is the standard deviation that is there. It's not the, so that's why it's universal. It's not, even if you can use weight to plot it or distance, but since you have converted it to z-score, you have look at deviation from the mean divided by standard deviation, it will give you z-score. It's universal, can be used. So if you plot anything, it will be like this, any variable. Now, that is why horizontally, you only see minus, -3, -2, -1, 0, 1. The mean is the 0. Now, it's bilaterally symmetrical. It has been established that in between -1 and +1,